So I'd like to make a plan for this. So we've seen a lot of things, but all of this is in the beautiful world of type theory and logic, where things are always nice, and we never talk about computation. And so now it's time to just break everything. And so I want to just, so we talked about STLC and CCCs, okay? And so STLC presents the pre-CCC, and if you ever find a mathematical structure which is Cartesian closed, it'll give you exponentials, and you should think about what it says about computation, right? So that's one way of thinking about semantics. So in the first two lectures, we talked about Cartesian closed posets and Heyting algebras, but I never gave good examples of CCCs, and it's I'll just give you a few right now. So every Cartesian closed poset is also a CCC, right? Because posets are thin categories. So the examples of downsets of P, which are the same as monotone maps from P op to 2, right? But posets don't have any computational content. So if you go from posets to categories, you need a similar construction. So I won't be able to tell you much about them this hour. So presheaves on C, which are the same as functors from C opt to set, right? So just like 2 is a nice classifying poset, sets play the same role for categories. And sorry? Yes, any small category is what I'm saying. Yes. Well, okay. So maybe that is a nice thing to say. So C op comma V. So V categories or V presheaves maybe. So if you know about enriched categories and things, that's one way of thinking about presheaves. And these are nice models because just like we saw the map going from P to downsets of P is a Yoneda map, which sends poset elements to downsets. And there are some nice theorems about them which show that they preserve the meets and exponentials. And you have a similar thing for presheaves, which is the Yoneda embedding, and it sends objects to the representables on. So there's a very nice analogy between downsets and representables into X. Okay, there's a lot about the Yoneda lemma. There are lots of textbooks, and you can learn about these things. And maybe one of the other thing that I mentioned was here every downset that I think someone noticed and talked to me about it is it becomes like for every S in S like this, and here a similar thing happens. So for every P in presheaves of C, it becomes isomorphic to a coend of at a colimit of representables of C. Okay, but we have to define a lot of things to make this very precise. So I won't go into it. Okay, so why are presheaves nice? Well, this embedding of P into downset of P preserves the Cartesian closed structure, and embedding of C into presheaves preserves the Cartesian closed structure. But on top of that, it's actually it's an embedding, so it's fully faithful. When it's fully faithful, it preserves equations. Okay, so if you have a nice model of lambda calculus, you can go into presheaves and you get another model, and these two models will prove the same equations on lambda terms. Okay. Okay. So these are presheaves, and then we saw that there were problems with sums and coproducts, right? And so then there are sheaves, which you can take sheaves on C, which are a subcategory of presheaves on C. And to give sheaves, you have to give a site and a canonical topology on C. And so that's another class of models. So 1, 2. Right, and then there are more interesting models, which right. Let me just say. So I did talk about. So VCAT is a is V enriched categories, and just like cat is Cartesian closed, VCAT is Cartesian closed. And if you take V to be your truth values, you get posets. Sorry. Oh, sorry. So if you. Oh, right. Okay. So if you take V to be truth values, you get posets. And now instead of truth values, you could try other things like take V to be, power sets of L, and you should. I'll leave this as an exercise to see what that gives you. It's a very nice model. Okay, we can talk about it afterwards. And the other class of models are ones that come from linear logic. Okay. So Jules talked about the category rel, which is this category rel, which has objects sets, and morphisms are relations. Okay, morphisms are relations from A to B, and rel is it has tensor products, it has linear exponentials, and it's compact closed. So if you give me rel, there's a way to build a comonad called a Sealy comonad on rel, and which turns linear maps into intuitionistic or nonlinear maps. So so if you take maps like this, you apply something called the so maps in rel like this. Let's see, and this becomes by the closure in rel, you get okay. So things of this form, bang A, lolly B, are exactly your exponentials. So if you give me a model of linear logic, you can encode intuitionistic things into linear logic, and this is the call by name Girard translation, right? Which is very very well known. Although it's done at the level of syntax, but at the level of semantics, it's a matter of having this isomorphism called the Sealy isomorphism. Okay. Okay. So if I have comonads like Sealy comonads, I can build CCCs, and then the other right. Okay. And if I said rel, I should also maybe mention coherent spaces, which are a refinement of rel, which is not as degenerate. And then coherent spaces and linear maps is a category, and on it you have a bang, which is coherent spaces and stable maps. Okay, and these stable maps are models for sequential algorithms, and yeah. So there's a huge number of CCCs that you can generate from linear logic models. And then the final thing is where you have effects, right? So when you have effects, maybe my notion of what it should be an effect is going to be, I take the simply typed lambda calculus, and let's say I add an effect like gamma derives print, or it prints just a character p, and I say that print has the type unit, and now I had this equation, the eta rule for units, which was f equals. Oh, sorry. Okay, so I had this eta rule for units, and now this is just not true because you know, I have print, and print is not equal to star. Right? Okay, and these are two different programs, and if I observe them at runtime, what star is going to do is different from what print is going to do. And if you like compilers, then your compiler now cannot optimize away units because there's no universal property of units anymore. Okay, so when it comes to effects, we don't have exponentials. We have partial exponentials. So we saw the definition of a CCC was a category C where you have a unit type, a and a function type. Okay, and these gave us all the beta eta laws, right? And so what should be a partial CCC? So the whole program of strong monads, the computational lambda calculus, was meant to axiomatize what is partial computation. And there are various ways of presenting what is a model of you know, lambda calculus with effects. The one I'm just so it's a category C which has products, and then there is a strong monad T on the C. So let's so 1 and 2 plus so when they were originally invented in the old papers, they say partial exponentials, but these days we just say Kleisli exponentials. Okay, and so every such category, if I have a monad on it, it has a Kleisli. So Chris talked about it a little bit about you know, monads have resolutions. So you have a Kleisli resolution where so CT of a comma. Oh, right. Sorry. Okay. Just becomes C A comma T of B. Right. So these are the programs that allow you, when you run the program, it can perform effects. So so giving me T is like giving me a way to perform effects when I run the program. And these so let's say so the third thing star is now, it now becomes CD of gamma times A. Oh, I should make it similar to so CT of gamma. Wait, I want to write the exponential on the left. So A L T of B. Okay. Yes.
A junction symbol?
Right. Yes, this is so let me write V and K. So V is left adjoint to K. So yeah, so what is V? So V is the inclusion of C into CT. So on the objects, it's identity. On the morphisms, it does exactly this thing. And K goes from CT to C, which takes objects to T of X. All right. And right. And C, so partial exponentials are where I would write gamma times A comma T of B. Okay. And so this is now a this is now a partial exponential or a partial function. And sorry. So I I already wrote a T here, so the T is implicitly in the Kleisli arrow. Okay, and so the point is now there's a category of values and a category of computations, right? And you could say that this presents a partial Cartesian closed category. And now we've seen many examples of monads, and if like a lot of these examples assume C to be a category like set, and CT is reader, writer, state, continuations, lots of good examples of computation. I did not say much about the strength, so so the strength is what makes the application or the function elimination rule work. And maybe when I write down an actual semantics, we'll see what happens. Okay. So okay. So very cool. But this is all axiomatic. So I can have monads on C. I can have comonads on C. But I'll show you a way of using some of the things that we've learned and using it to build a very fancy category C, fancy C, which has both a monad and a comonad, and they're going to interact. So, okay. And this is where the ideas of Kripke semantics comes into the picture. Let me just start from, let's say, so I want to type the print, effect. So if you have ever programmed in C, to print something, you need to get a file pointer, right? Say P, a file pointer, and let's say a string. So I print S on this pointer P, and this is a unit. Right? So to print a string, I really need a free file pointer in my context. Okay, and so very informally, what this means is if there is a p colon file pointer in gamma, then and if gamma derives e colon unit, I should not be allowed to perform an eta conversion because it might have print effects. Okay. If p colon file pointer was not in gamma, there's no way I can type print because I don't have a file pointer. So this should be star. Okay. So there is some way in which capturing variables in my typing context should be a way of distinguishing pure and impure computations. And if I set up my typing rule for effects in a way that allows me to make this distinction, that's what that would be a really cool thing to have, right? Okay, and right. So this is in the syntax, and probably I should now mention something about weakenings. So you see that we did a bunch of things like if gamma weakens to delta, and delta derives E, then gamma derives E colon A. So under weakenings, typing is invariant, right? And so if I can type something in a smaller context, I can type it in a bigger context. So if and similarly, the membership judgment has a similar thing. And so what this is saying is there is this thing where gamma varies, right, to delta and so on as a subset relation, right? And at some point I capture a pointer p, or I open a file and and my context now has an unsafe pointer, and then if I know that at some point my context becomes gamma prime p colon pointer, then the same. So anything above that is going to be an unsafe computation, right? But anything below that will have the same state as the things I started with, right? So right, yes.
This constraint is in file pointer is not included in gamma. So what you're really saying is that there is no way of constructing the file pointer in gamma. Is that what you're saying?
I haven't said what non-membership is, so I need a.
Does that have a function in return to file pointer? You don't have a file pointer directly.
Right. Yes. Right. So so this is very informal when I say not a member of gamma. There's really no way of saying things like that. What I need is a way of distinguishing contexts which are okay, this picture is fine. So now there's two things to do. One is to think about semantically what these things mean, and syntactically what these things mean. Okay, so let me start by doing a little bit of what we've seen already. So I'll define a so I'll fix some set of names. Let's say which is, let's say, p. Okay, p is a bad name because I want to take power set. So let's say c for channels or pointer names. Yeah, right. Okay, and then and then I say that my objects of some so I'll construct a category over C where I say that the objects are going to be sets. Okay, and now here's one way of writing it. It's a forcing relation which says a. Let me write the subset thing. So a c times a. Okay, so it's a relation which says give me a channel named C and a point in this set, and I'll tell you whether or not this value captured this channel. Okay. I should mention that Bob Atke showed similar models in the implicit complexity class, right? Yes, sorry. Yeah, I'm building a semantic model where I can talk about unsafe pointers. Okay, yes. Right, and these. So here's one of the tricks I showed earlier was to turn relations into so you can think about down sets and they become just functions into two. So I'll turn this Kripke relation into a function, let's say, from A to power set of C, because C times A to 2 is the same as A to 2 times. Sorry, 2 to the 3. Okay. So power sets are functions in the bool. I turn them into these functions. And so I will write it like this. Okay. And I want them to be monotone. So maps between Okay. These are going to be functions. Such that for all inputs, if you run the function, it's going to so if you captured a pointer at A and then you run the function, the set of captured things should be a subset. So you're not allowed to capture new things. Okay. Right. So this is a very concrete way of writing this whole thing. I will. So these are kind of okay. So these you can think about them in two different ways. One way is to think of them as Kripke sheaves. Okay, and where I'm taking power sets on C, and power sets are a complete Heyting algebras, which so it comes with a canonical topology. And the other way is the kind of thing that you like here, which is containers, which is you can think of them as fam of this with the superset relation. So it's a free coproduct completion of something, like containers are fam set of. Okay, so so those of you who know about these things, so you should so just like in the previous lectures we saw maps like this, so you should try to define for a complete Heyting algebra H, which is power sets. You should try to define H2 and H, and you should observe that it preserves meets and exponentials, but it gives you coproducts and disjunctions for free. Okay. Right. So this let's name this thing. Let's see, C indexed by C, something like this. Okay. And now this is very much similar to a Kripke model, and you can easily check that this C has products, exponentials, coproducts. There is an operational way of also trying to understand them. So if I want to take I take products of the things on the left, okay, and the things that captured the things that were captured by A, the things that were captured by B, just do a pointwise union. So so W A times B of A comma B should be A. Okay, and there is a formula for the exponential, which is also pointwise. But to do it pointwise, you should use the exponential in the Heyting algebra. So I will leave that as exercise and coproducts as well, but these are free. Okay, so so here's a model of the lambda calculus, right? Because it's a STLC plus coproduct. Oh, sorry. Okay, and I can make sense of the lambda calculus with all its eta rules in this category, right? But the extra information I have is what does each type capture? Okay, so so it's a model of STLC plus coproducts, but now I can build some fancy monads and comonads on it. Yes. So so yeah, sorry, 0, 1. 0, 1 plus times exponentials. All of these have, yep. Okay. Right. So so all of this is standard, and this is fine. And now I can define a monad on C. A monad on C. So we're trying to model print, right? And so I'll take the writer monad, and now I'm having. So the writer monad should give you the same things times an output function, right? So I need a C, and I need my sets of channels and my sets of strings. Okay. So it is. So the object C that we started with it sits inside this category C of C. Okay, and yeah, sorry, yes, yeah, maybe should I just call them CH channels? Yeah, the names of the channels or file pointers, yes. And so you pick this thing to be so what is the representing object of CH? Well, it's the same set CH, but you have to define this thing from CH to power set of CH, and just take the singleton. Okay, and then this is just a base type, so it's just a set of strings. Okay, and so this is the mapping on objects. And objects are two things now. So I have to give you a W of Tx, right? So your W of Tx should be a thing from X times channel string to power sets of channels. And now you have access to this output function, and you have access to the things that were captured in X. So you say you have X and an output function. You take everything that X captured, right? And you say, well, look at all the channels and what you printed on them. So if so I want to return a C if output of C is not the empty string. Okay, so so I have an extensional access to the things that these channels are doing using this output function, and my semantics says I will track those channels, which actually did something. So I actually used those variables. Right? Okay. So this is a monad, and it requires some checking, right? Okay. And then there is a comonad, which says I will pick those X and X for which this is empty. Okay. And you have to give away to a box of X, but this would just be the empty set. Okay, so because I've been tracking the pointers, I write down a functor on this category of Kripke sheaves or whatever that allows me to just completely drop all the unsafe things. Okay. And now a fascinating thing happens, which is that if you know that you've done some computation using sorry. Okay, and now this thing where you do some computation and you box it, And from this, you can just go back to box. And this is a natural isomorphism in A. So T of A says, yeah, these are all the channels that I'm going to use. And box says, no, you cannot use any channels. And these two things cancel out. And yeah, that's the strongest thing you can say. So at the end, you'll still have no channels. So yeah. Okay. And so this is the semantic story. And okay, so one more thing, which is now you had your CCH, right? Which has T, which has box. Okay. Sorry. Right. And you build this new category C, let's say with box and T, which has the same things as C, but you set the morphisms to be box A to T of B. Okay. So you allow computations on the right, but you disallow computations on the left. And so it has. So if you want to compose these two things, you go. So I did not maybe say things about the strength and stuff. So this is actually so just like monads are. So this is a strong monad, and this is a strong monoidal comonad, as in box. So first, so a comonad has box A to A, box A to box square A. But for this comonad, doing the subset operation twice is the same as doing it once, right? And then A times B is the same as box A times box B. So the fact that it preserves products, what allows me to move it around in context. Okay, and now if I want to compose these two things, I go box A to box A. I apply box F, which gives me box of T of B, and then I do a cancellation, which gives me box of B, and then I apply G. And this is why substitution works. If you believe me that substitution is composition, this is the thing. And now the final thing is. Oh, sorry. Yeah, I don't get to see the thing behind me. So right. So now you've got this. So these are the things in right, and okay. So CCH, and because this category now this is a partial exponential in CH. So and now I actually do the exponential. Okay, and now what was I going to say? Oh, right. So and this is what? Okay. So now I right. So now I treat. So this is my final encoding of translates to box A to T of B. Okay, and if I do this, I can use the the Cartesian closure in CH to get back call by name functions, lambdas. Okay, so this is the semantic story, and now if you run the categorical semantics of Cartesian closed categories, and now you have to take all this structure and actually tweak your contexts and judgments to make it work. So so going back to the syntax. So okay, I lost it. So I have to distinguish between contexts which are boxed or unboxed, right? So I say that there is a P operation on contexts. Okay, so the empty context is a pure context. Okay, and then I take x colon pointer and do this operation here. I actually drop these things, okay? And if I do x colon a and do it on this, okay. And if you change your contexts, you have to also change your substitutions. And so we have substitutions. Well, I wrote this, and then theta. So when we have partial exponentials, we're only allowed to substitute values for variables. So these are the impure computations, right? And then when I actually have pure computations, I can have a third kind of substitution. Okay, and now the substitution judgment becomes empty context. Okay, and if I know gamma derives delta comma. So this is my impure call by value substitution, and now I have a different comment where I can say if I know that E is pure and right, and so this is how you set up the structural rules, and you have so you have your typing rules as star. Get it? That's fine. And you have a print s. Get it? With the appropriate channel. Right. And your functions are allowed to capture impure things, right? So impure functions which return partial exponentials. So okay, but if you know that you have an expression which is typed in a pure context, you can reflect it back using your comonad. So box A. So the box is a type constructor I add, and let's see if I can write so this is the box introduction, and let box x equals E1 E2. Okay, so I know that gamma derives E1 box A, and if I capture A, so pure computation, then I can actually eliminate. So these are the so it's so we had to like change the judgmental structure, right, by changing the kinds of contexts, right, with the operation on contexts. And when you write the introduction and elimination for the box, this operation gets reflected into the syntax, into the into your types, right? So now I can type pure computations inside a impure language. All I have to say is right. Sorry. Yeah.
What is the P operation on gamma doing again?
It's dropping exactly these impure pointers.
Oh, okay.
So
Thank
in
you.
the semantics, it is exactly all right. And so right. So typing rules for these things go like this. So it's a mode which lets me distinguish between pure and impure computations inside inside types, and then so now there's an equational theory for these things. So the full equational theory requires a lot of work. All I'll say is just that this this holds that gamma pure derives E equals the unit type. Okay, and sorry.
Just
okay, right, and right, and you can recover eta laws as well. So that it's a pure function, which means if I'm forcing f to be pure, it means it cannot capture anything, right? So so I get back eta laws for functions and all the other things, and now I can translate the lambda calculus into this. So let's say the translation of the function type will be A to B, where this is my partial function type, and on terms you follow the same thing, and you follow what the typing rules say, and then what you get is if you can derive E1 equals E2 equals A in the pure STLC, then the translated things will be equal in this lambda SVH. And so now as a programmer, if you want to reason about pure computation and tell your compiler, okay, you're allowed to optimize this program because I know it's pure, you have to type your program with this box type, and that's yeah. So I'll just stop here for questions and comments.
You mentioned that we need the equational theory here.
Yes.
Why do we need the equational theories here?
I wanted to show that you get back all the eta rules for pure computation.
Oh, okay.
So and you use the semantics to actually design the equational theory in that way. Yeah.
Can I see the previous paper for us?
Yes.
Just a second. So like typing judgment with P annotation is for like pure computation, right?
Yeah. So wherever you see a P on the
It's a pure
yes,
computation.
yes.
Oh.
Yep.
I had a question. I think this is a few slides ago still,
Okay.
where we showed the interaction of the monad with the comonad.
Okay, but you can just ask your question.
The one with diagram where we compose a box.
Yeah,
into
compose.
TB.
Yes. Sorry. Yeah.
Yeah. So you said if I put a box around a T, that's basically saying box says you can't use anything, and T says what you're using.
Yeah.
So if I put a box in front of a T, does that force the computation to be pure?
Yeah.
Okay.
So it becomes isomorphic too.
But so then where is there any chance to have any effects in this composition?
Yeah, there isn't, and so the subcategory, it becomes Cartesian closed again. So you literally just drop all ways of doing impure. Yeah.
Okay.
So without the box, this
Yeah.
allows you to do stuff, but you add the box. So you cannot just box anything, right? Yes. Right.
Okay.
Yes. Yeah. So you could say something stronger, which is like box of A arrow B. So go inside and just make sure there is no application which can actually do. Yeah.
Ahead of time. There's still some time for questions. Okay, we'll be back.
So this is probably a related question, but so I'm not sure which monad did we define. Is there any kind of concatenation, or are the results of the output of F replaced by those of G? Because I don't see where we use a concatenation of.
So the mu of the monad will have to do concatenation of the strings.
Okay.
Both concatenations. Yeah. So that's standard for Rider monad.
Okay. And so, but in this composition, I don't see how we get the effect of F, since we apply it.
Yeah, so F is under the box, right? Here, so F is applied here, G is applied here.
Yeah, but since there is a box in front of F, we still have its effects.
No, so wait, so F is under the box, yeah, because it's a functor.
Okay. But the fact of applying the functor on F does not, we still have its effect?
Well, so A to B, box A to box B. So if you restrict the inputs of F to only the pure things, so it's only allowed to act on the pure things. Yes.
Okay, so the functor just restricts the input, but keeps the effect of F.
Yeah.
Okay.
But F is only acting on the subset of inputs that are boxed. Yeah.
Okay, understand. Thanks.
Are there any further questions? Recording.
It looks from that diagram, right, of the composition there, like there should be a sort of dual way to compose where you rather than using the co-multiplication and the unit, you use the multiplication and the co-unit. Does that give the same result? Would that other leg of the diagram
to check,
commute?
but I can give you. I haven't told you what the axioms for phi are. So So it's like it's a just like you have distributive laws, but you have coherences for distributive laws. So phi comes with some coherences. Yeah. So if you use those, we could check.
Okay, thanks. So I think in the interest of coffee, we take the other questions.
Okay. Yes.
And thanks
Okay.
again,
Thank you.
Vikraman, for